Welcome everybody. This is Database Systems Lecture. My name is Jens Dittrich. Happy New Year. Today we will be continuing with query optimization, in particular query processing. So before Christmas we talked about plan enumeration, cost-based optimization, rule-based optimization, the query graph, and how all these things fit together. Today we will be talking mostly about query processing pipelines, how to organize data in the query processing pipeline anyways. So with that, let's start. For questions, I am available on our Discord channel, in the text channel, but also in the break. And after the lecture, I will be available in the audio channel. So we will continue with query optimization today, mainly focusing on operator models, pull versus push, vectorization, which is an unlucky name, which we will go into that, basically means batching. Rule versus cost we had last time. We don't look into that too much. So today it's mostly about the operator models. So what's important to know about operator models? Well, let's first go back to where we are in the lecture. So basically what a query optimizer does is you have some declarative SQL statement here depicted on the top. Then that is fed into the query parser, which feds an intermediate representation of the query into the query optimizer. The query optimizer uses a catalog. The catalog contains statistics, metadata, which tables exist, what are the attributes available in those tables, stuff like that, but also statistics for cost-based optimization. The query optimizer uses that catalog and then creates a plan. And then there are different options to executing that plan. So one is to rely on pre-compiled modules and then interpret the plan. That's one path. The other is to actually generate code. Yeah? So similar to what a C++ Rust compiler would be doing here, and then execute the code. So we will be looking at how that works in more detail. So again, the story so far was something like that. We have SQL, that's the input, and we were here. So basically after cost-based enumeration, after cost-based query optimization, we have a plan. We have an idea on how to execute that. We know, okay, we do an index seek. Yeah? In this query, we want to have all the attributes, all the tuples from A, where A1 equals 42. That's here part of the where clause. So that ends up in this bubble and this leaf in this physical execution plan. We have a scan, we have an index sequential access method, access here, we have a filter, stuff like that. That's our physical plan, that's what we have. And now the question is, okay, and now what? What do we do with that plan? And that's what we will be looking at today. So the question is, how do we execute that? And so I put the same plan on the left, and the question is, what do we do with that? Well, we could basically translate that into a big function call. Yeah? Imagine you have, if all of those are functions, you have a function performing the iSeek in your programming language. Performing a scan, it's basically a function call, and that's basically a big function call graph. Yeah? So here's something like that. That's basically what you will be calling. You're calling the simple hash join function with the following parameters. Each parameter is a result set returned by one of these other functions. So the innermost function here, if you look at that, is a scan. The scan on relation C returns, relation C. If it's a terabyte of data, that will be returned, will be passed to the next function, and so forth. So basically, it's nothing but a big function call. But the problem with that is intermediate results. And to illustrate that, we will look at that query in the following. So again, that's a query that's a plan that was generated from that SQL statement. So we have an index access here, we have a sort operator, we have a scan, we have a merge join. So recall the merge join requires that both inputs are sorted. And we have a special case here already that one of the inputs is sorted already on the join key. That is due to this ISAM access, scanning the leaf level of a B tree. We looked at that in the indexing lecture. Basically, it's already sorted along the right attributes, so there's no extra sort operation required anymore. So we only put an explicit sort operation here. After that, this left input is sorted, the right input is sorted anyway due to ISAM, and then this is only performing the merge join without the sort. Whatever is produced here is the right input to the simple hash join. Recall a simple hash join. How does it work? It creates a hash table for the left input. Yeah, so everything that's read here is put into a hash table in the simple hash join. That's also called the build input. And then everything that comes from the right input is probed against that hash table and produces results eventually. So that's a plan we will be looking at in the following. Yeah, and the question is, how do we do that, in particular when it comes to these intermediate results? Of course, if you materialize intermediate results, as you might be doing in a function call, this stack of function calls, maybe that's not the best way of doing that. And so if you think about how to organize that in a pipeline, I really depicted it as pipelines here, it might look something like that. Well, so you really have here the data that somehow flows from bottom to top. It flows from these three sources of data we have here. That's three inputs to the pipelines. And the pipelines somehow combine the data that comes up from the sources and eventually emits the output here. That's basically how you could draw the pipeline. Well, that looks fine. Maybe that's how it works. But the problem is, well, some of these operators need to buffer the data that comes from underneath. So if you look at this here, you see, well, in order to sort, how can you sort data? I mean, just in order to determine what is the minimum element, and in any given set of data, what is the smallest element if you sort in ascending order, you will only be able to do that if you have seen all the data. So there's no way that you can just inspect parts of the data that is delivered by that scan. Just the first 10% of the data sorted and emitted to the merge join. That is not necessarily correct, because the very last element available from the scan, delivered by that scan, may be the minimum element. So over. So in order to be able to determine which is the first element in the sorted stream of data, you must draw all elements. You must inspect all the elements available in relation C in this situation. That means basically, conceptually, what the sort operation has to do at this point in time is it has to inspect all the data, and programmatically it has to buffer all the data. It has to, if this were water, it has to create a big water tank where all the data is put and stored until you have seen the first minimum element. So that this is really blocking the pipelining property we were expecting. You can't pipeline anything up until you have seen everything here. In a similar situation, you observe in a simple hash join. Here you see, okay, how does it work? You remember simple hash join first reads the entire left input, creates a hash table, and then probes the right input against that hash table. So when you start with a simple hash join, it will read everything from the left and put it into an intermediate, into its own hash table. But basically, that means it buffers all of the data that comes from its left input in that hash table. So that's again a blocking behavior. The data is not really flowing through the pipeline. You're actually buffering and storing a lot of data in certain parts of the pipeline. And this blocking behavior is available for some operations, but not for all. So for instance, if you look at a filter operation, like a selection in relational algebra, the filter operation is decided on a tuple per tuple basis. And once you see a tuple, you can decide immediately, given a selection predicate, whether it qualifies or not. So once you find a tuple that qualifies, you can immediately pass it on. But at no point in time there's a need to buffer or to store more than one tuple in a filter in this world. It doesn't make any sense, because you can decide immediately. Once the tuple arrives here from underneath, you inspect it, and if it doesn't qualify the filter predicate, where you throw it away, you ignore it. If it qualifies, you pass it on to the next operation on top. So there's no need here to buffer elements. In contrast, for sorting, there is a need to buffer elements. For merge join, similar situation. If you ignore the sort operations, if the data is already sorted, there's no need to buffer more than a couple of tuples. Yeah? Basically, you just have to know what is the next tuple from the left input, what is the next tuple from the right input. And based on that, you can try to find a join weight. So bottom line, there are different types of operations. Some of them have to inspect all the data from underneath, or some of the data from underneath, and others don't. And yeah, if you look at how such a pipeline operates, here again is a visualization, because you can identify different stages. If you recall simple hash join, what happens if you initialize simple hash join? Well, you first fill up that hash table. That is basically, here I open the valve here. All these two valves are closed. So that's the output valve, that's the right input, that's the left input. So the left input is open, and it will be left open until you read everything from the left input. Yeah, now the left, so on phase 2, the left input is exhausted. That's your hash table. That's what you buffer. And then you run into this probing phase. Yeah, this probe phase where everything from the right input is probed against the hash table. And if that produces a join result, that join result will be sent to the next stage in the pipeline. Those are the three stages you can identify here. So if you look at for quick sorting, how would that work? I mean, again, sorting, any sort operator, no matter whether it's quick sorting, external sorting, heap sorting, whatever, principal problem of sorting is same as for an operation like give me the minimum element or the maximum element in the stream. Well, you first have to inspect all the data that basically happens here. It reads that, eventually it has read all the data, then it can start sorting. Or if it's just a matter of identifying the smallest element, it can scan once through those elements. Maybe you keep priority queue for that, whatever you want to do. But then basically you can output the elements or the elements in the sorted stream one by one. So those are the stages in a sorting operator. And for external merge sort, how that is typically done is in the first phase where you read the data. It's not that you organize your algorithm that you read the data, put it on disk, and then eventually comes all the magic of external merge sort. Now what you do here is you read the data, and while reading you already perform this phase 0, this run generation phase. Yeah? So with the available main memory, yeah, you either use quicksort or replacement selection. We had that in the lecture as well. You write the initially sorted runs. You do that until the input is exhausted. Then you close that valve. Then we are in this situation. So we have all data available, already organized in runs. And then what you do in the second step is you start merging until there's only one merge left, the final merge left. So basically you sort and merge until you're ready to produce the sorted elements. So only in this third phase, when you really need to output the sorted stream of data, then you run this final merge in external merge sort. That's basically how you can split that into 3 phases. Okay, so here's an overview of the different operations. So basically, simple hash join, or simple hash join, as you should know, is a special case of index nested loop join. We talked about that as well. So this join operator is blocking with respect to its left input. Yeah, so it doesn't do anything. It first has to consume its entire left input. But then once that is done, once the hash table has been built, the right input is probed without blocking. Yeah, so you can draw tuples independently from the right input, probe them against the hash table, and if there's a join result, there's a join result. You pass it on directly to the next stage on the pipeline. So it's blocking with respect to the left input, but not with respect to the right input. The same holds for bulk loading. So what the simple hash join does here is basically it bulk loads the hash table. Yeah? So if you do bulk loading independently on an index, well, that's blocking, yeah? Because you bulk load the index. The same holds for sorting. Any sort operation is blocking. Non-blocking is the probing part in simple hash join. So once you're on the phase where you look at the right input and probe it against the hash table, any kind of merge operation, non-blocking. In particular, the merge join. So the merge in external sorting, the different merges are non-blocking, but also the merge join without the sort part is non-blocking. Same is true. The same is true for a filter operation, the selection. The same is true for projection. Yeah? On a tuple per tuple basis, you can directly pass them on. No need to inspect the entire input. And that's another join we didn't look at. That's called double pipeline hash join. Let's ignore that as a fancy join. Not important here. Okay, so here's an alternative representation. Just for the fun of visualizing it, here I drew the water tank in the middle, but whatever. So now the question is, how do we really implement that? That's the interesting part. So how do we implement such a pipeline? So we want to do pipelining, but how exactly is it going to work? So you may have heard about pipelines. For instance, in any Unix-style operation system, you have this a pipe symbol, and then you can pipe the output from one shell command to the next. Yeah, that's one implementation of a pipeline. But the pipeline we're talking about here, for the moment, is just a concept. I'm just saying, okay, I pass the stuff on from one operation to the next, but we haven't decided on how do we actually implement it. That's something we still need to talk about. And there are many options for doing that. And let's talk about some of them. So one is based on what we call operators, or maybe if you heard about iterators in Java, or many programming languages have iterators. That's basically the idea we're talking about here. So it's a very simple interface. It's called the ONC interface, open, next, close, because it only has 3 methods, and that's all you ever need, basically. So, and the interface, maybe let's first look at the open and the close method. So the idea of the open method, or the contract of the open method, is as follows. It initializes an operator. So the idea is that we wrap certain functionalities in bubbles, and those bubbles are called operators. If you go back to our pipeline, so what I will do in the following, I will say each of these operations, the merge join, that will be converted into an operator. The filter will be converted into an operator. The scan will be converted into an operator, and so forth. So any kind of meaningful algorithm that I will run here as part of such a query plan will be turned into an operator. In the end, I have a tree of operators. And the contract of those operators is as follows. So I say, okay, there's an open method. It initializes the operator, does all the work necessary to be able to compute the first result. The inverse to that is close, so it performs the cleanup work if necessary. So closing files or something like that, closing a network connection, whatever, deleting temporary data you might have created on the way, stuff like that. The interesting thing is this next method. So this is can be called from outside, and the contract is it returns the next chunk of data. I didn't define what chunk is at this point in time because this operator interface is orthogonal to what a chunk is. Typically in databases, the first time you learn about that, we will assume that a chunk is a tuple. Yeah, so if you go back to our visualization here, so you could run a pipeline such that you assume that these operators pass tuples around. Tuples are transported through the pipeline, but we can have smaller granules, but we will also have bigger granules later on. So it's a parameter you can define in your query processing. So if you look how such an operator can be found in programming languages like Java, here, this is an example how it looks like in Java. There's in java.util, it's an iterator interface. It has been there from the early 90s. They created that already in very early versions of Java. So you don't have an open interface, but you could do that in the constructor. Yeah? So an object-oriented programming language, basically the constructor, that's the job of the constructor. You initialize that instance, and that's what the constructor is all about. Yeah? So maybe you can leave away the open method. And so here you see in the iterator interface, there is no open. Then in Java, you have something like has next and next. So has next basically is a method that you can call to ask such an operator, such an iterator, whether the next call, the next call to next returns a meaningful element. Yeah, so you can ask the iterator, hey, do you have a next element for me? So you call hasNext. If that returns true, then you call next, and that will return a new chunk of data, a new tuple. And this is a bit unlucky, the separation, because typically when you try to implement that, you quickly find out what, in order to determine whether there's a next element, you very often have to actually compute that element in the first place. So actually all the work is done in that hasNext method implementation rather than in the next call. So in the following, we will leave away this hasNext. We don't do that. We directly call next without calling hasNext before that. And if you don't have another element that we can return, we could either throw an error message or we return null, for instance. That would be one way to organize that. The close method is also not available in the java.util.Iterator interface. You could do that through some sort of destructor, but that may be shaky. So better is to have an explicit method. And there's another method that's the remove method, but we won't need that in the following. So basically, my message is we will stick to an interface like that. That's all we need. So we have a clear semantics in the sense that's open. So really initialize your operator to be able to compute the first result, to be able to serve next calls that are coming up. So basically how an operator is used is always there must be one open call, then an arbitrary number, so from 0 to n, next calls, and then there is one final close call. Once the operator was closed, it cannot be opened again. That's basically how you use an operator. And I will show concrete examples in the following. So if you translate that into pull-based operators, it will look something like that. And so basically you have a user here, and then that calls on this tree of operators. So each method here, the simple hash join, was translated into a simple hash join operator. The merge join without the sorting was translated into a merge join operator. And now the user calls open on this top level operator, on the root node of this binary tree. And then the user calls next, and then the user calls close. So in more detail, here's an example how that would look like. Again, I use the assumption here that a chunk that is passed around by a next call corresponds to one tuple. So the user will be calling open first to initialize the entire tree. Just a short okay. So the user will be calling will call open on this topmost operator. And then recursively, that operator will trigger certain actions. So it will, as you might expect, call open on all the operators in the tree. But actually, it will also, in most cases, do much more. So you see each of these operators available receives an open call. And you see that I wrote down the calls on the edges. Yeah? Basically, the user is calling along the edge this operator. So it calls open on this operator. And the same happens here recursively. So the simple hash join will perform its build phase, which means it will fill up the hash table. So in other words, it will draw all elements from its left input. So it will not only call open on this iSeek operation, that happens here, it will also call next several times, and then it will call close. That's how you could organize it. You could organize it differently, but that's typically how it is organized. So we have one call to open. Yeah, how many calls do we have to next? Well, that basically the number of elements that qualify under that condition, depending on the selectivity, of course. So I wrote it down as the selectivity under this condition times the cardinality of A. That's the number of next calls the simple hash join will be issuing in its open phase in this scenario. So you do all of that work. Eventually, you build up the hash table. Then you proceed in the recursion. You call open on the merge join. It calls open for its children, and so forth. Then sort in the open, as explained before, an external merge sort. All the data will be read, all intermediate merges except the last will be done, and so forth. And that's maybe similar maybe similarly done in other sort implementations. So basically, you want to be able to quickly deliver the first result to next. But in the end, it means all of C is read here, is kind of somehow buffered in the sort operator. And that all happens just because you call open here on the topmost operator. Now, once the first next call is issued by the user, and that's this scenario, so the user calls next for the first time, nothing happens on the left input anymore because we did all of it already. We exhausted that input. But now we need to call next on the right input. We need to probe the hash table here. And that can trigger a couple of other recursive calls. And that's hard to quantify how many, because this depends heavily on the selectivities, obviously. So if you call next here, the simple hash join has to produce a join result. In order to produce a join result, you have to get input from the right input. Yeah, but how many? I have no idea, because I don't know. It doesn't have to be true that each element here matches an element here. Yeah? So maybe you have to draw a couple of elements before being able to identify the first join result here as a simple hash join. Yeah? So you see where that leads to. So basically, you call next here, then you call the first time next here. Well, now the merge join has to determine its first result. I don't know what the selectivity is, but in order to compute the first result, it has to draw elements from left and from right, interleaving drawing from left to right, until eventually it finds such a result. So the question is, what is y2, y3, and y1? So I mean, I can give boundaries for that, but it depends on the concrete situation how many calls are being issued. So if you just look at y2, I wrote it here, that is the worst case is the number of elements in C. So I draw all of C, all of the input, everything that was stored here, plus 1. Y plus 1. Write it in the Discord channel. Why isn't it the number of elements in C simply without the plus 1? Why did I write plus 1 here? If you have an idea, write it in the lecture channel. Yes, to know that this is the last one. So the last time so the contract here is typically the operator doesn't know how many elements exist underneath, not without extra knowledge about statistics. But you will be calling next until a next call returns null or throws an error, however you implement that. And that's the last time you called next, and that's the plus 1. So you call next for each tuple plus the last time where you get the signal, oh no, it's empty. Yeah, right. That's where the plus 1, why there's a plus 1. And the same is here for this y3 part. Again, I factored in the selectivities plus 1. Well, this is interesting. Why is that? This is because you should answer that. Why is it limited by y2 times y3 plus 1? Plus 1 is clear, same thing. Yeah, last element, last join result. There's no more join result. So what, but why is it y2 times y3 in this merge join? As a worst case. And that's the number of elements. Of course, there's one call. Yeah, there's at least one call. So the minimum is you have one call to next here, this next call to the merge join, returning null. So there is no join result. Okay, then it's over. That's the minimum number of calls you have. And the maximum number of calls, I claim, is y2 times y3. Why is that? Someone has an idea? Yes, again, that's true. Maybe because the predicate is always true. Yes, it's the worst case in the join. The worst case is the join is non-selective. Basically, it's equivalent to the predicate is always true. Yeah, it's like building the cross product. Yeah, that's the worst case. So without knowing more about the selectivity, I mean, in a condition like that, based on some foreign key economy, you will never have that. It's impossible. But if for an arbitrary condition, worst case, it's a cross product. So that's the only upper bound you can find here. Great. Yeah, that's basically those calls that happen down the tree, and you see there are many, many calls. And as we're organizing this pipeline on a tuple per tuple basis, many, many calls will be issued. So here, just for completeness, there are many, many interfaces in the different programming languages that do stuff like that. If you program with Java and try to connect your program with a database using JDBC, JDBC is that interface allowing you to connect a SQL database to your Java program, then you get a result set interface. And that looks a bit different. Conceptually, it's the same thing, but it works slightly different. It also has an open and a close method, as discussed above. But the next method doesn't recall the actual chunk of data, the actual tuple. The next method moves the pointer forward. So also a little bit like an STL and boost. So it moves the pointer to the next chunk, and it returns true if that is a valid pointer position. So basically, if it's false, there's no valid pointer position, it's exhausted, no more elements. And then you have separate methods to retrieve the individual attributes from such a chunk. So in more detail, it looks something like that. Result set assumes the row. You iterate on individual rows. So you move the pointer to a specific row, and then you can call a method like that. At the attribute at position 3, return that as a string, or return that as an integer. Now that's basically how a result set is organized. And if you look at that in Java, you see there are many, many methods for all the different types, allowing you to retrieve the attribute values. Yeah, here's another thing how you could do that with columns, but I think we can jump over that. So basically, what's often confused in these interfaces is the granule of iteration. So most of these interfaces implicitly assume you iterate over tuples, you iterate over columns, but why would you do that? Yeah? So you could iterate over, for instance, pages. A page, assume a row layout. Assume the page has whatever, 42 tuples. So why would you iterate over individual tuples if you can iterate over entire pages? Yeah, the same happens with whatever, the postman. The postman keeps hundreds of parcels in his or her truck, and then on the same drive distributes the different parcels. So why the postman would never just put one parcel in the truck and then bring it to your house, return to the post, the parcel center, how that's named in English, and then picks the next parcel and bring it to the next customer. That doesn't make any sense. So you try to iterate over bigger chunks of data. And one confusion in database literature is that there are very different names for that, as usual. I mean, the best name for that is called batching. So I don't want to process on a tuple per tuple basis. I want to process on a batch basis. And the batch is typically a collection of tuples. It can also be a collection of columns, but typically what we are processing in these iterators are collections of tuples, called a batch of tuples. Yes. So let's look at some example implementations. There's some pitfalls you quickly run into once you try to implement those operators. And here's an example. So let's stick to this very clean, conceptually clean interface. Again, we have chunks that should be returned here. How would we implement that? And for simplicity, I assume that a chunk is a row, a tuple. So we're iterating on tuples for sake of simplicity. And that's how you could implement that in the Java-style notation. So if that is a projection, well, what's the feature of a projection? Projection operates on another operator. So it knows about an input operator that obeys that interface, and that's passed in the constructor. So here you say, oh, that's my input. Yeah, that's an input operator. That also is an operator, so it implements that interface. And the chunk granule is row again. Yeah? So that's the input we're operating on. This is a function we use to project. also defined against this row type, and I just assign it here to the attributes in that class. Yeah? So basically that's done here. That's here. Well, then I have an open method. What do I do? What do I do to initialize the projection operator? I don't have to do anything, but I should pass on the call, yeah? Because the open calls must traverse and must reach all of the operators in such tree. So I pass the open call on to my input. That happens here. I call input.open. The same happens for close, of course, recursively. Well, and then what happens here in between? If next is called, I draw the next element from my input. I call next on the input. If that is null, so that's this branch, I return null. So basically the input is exhausted, then I can't project on that, so I return null, and then the caller knows, okay, it's over. But if whatever I receive from underneath, from the input, is not null, I return that element projected. Yeah? So basically I assume that f is a projection function. So basically I just use as an input this row, that's this row here, drawn from the input. I put it into the function, and whatever is returned by that function, I return. Yeah? So basically with such a function you could also implement an arbitrary map operator. Yeah? It doesn't have to be projection. So I just assume here that the function is implemented in a way that it leaves away some of the attributes, but you could basically implement any map operator with such code. It's the same code actually. Yeah. So how would that work for a selection operator? So again, selection operator has an input that happens here. It has a predicate. Yeah, so I assign that. Open is also called on the input. Close is called on the input, same as for the projection. And if next is called, well, I iterate over the input. So input.next, input.next. Yeah, as long as it's not null. And I try to find out whether that qualifies under that predicate. So here I have a predicate, which means the function returns either true or false. If it returns true, I return it. That's what I'm doing here. If not, I continue with a loop with the iteration. Yeah, so that's basically how a selection operator would be implemented. Well, there's some quirks you will find when it comes to loops and operators. They have to be careful. So here's an example of a enumeration operator. You could also call it an enumerator. So what does that do? It basically, its goal is it should return, similar to range in Python, it should enumerate integer values from a starting number to an end number. So from 1 to 42, both including in this case, and you could pass those interval boundaries in the constructor. Now you call open, nothing happens. Close, nothing happens because there's no input operator. But then what happens when you call next? You could just initialize that loop with the from value, check the condition whether you're still within the range, and then you increase it after the loop and return the current value. But of course the problem with that is every time you call next, you will reinitialize this loop variable with the initial value of from. Yeah, so if you specify the range, say you want to count from 7 to 42, every time you call next, you will be receiving 7, 7, 7, 7. Yeah, and it will never end. You will only receive 7. So loops do not work like that. You have to do some extra work. And the simple trick is the state of an operator has to be maintained as an attribute of that object. So the change you have to do, if you go back and watch it carefully here, so previously we just kept the from and the to, so the range we should return eventually the range of integer values. Now what I'm changing here is I also keep the current value. Yeah, the current value, the current state, the current or the last or the next value. In this case, I should return. So you see it here in the implementation. So I change open to initialize current with from. Then in the next method, I check whether I'm still smaller or equal than the boundary. I assign, I create a variable and assign it with what I want to return next, and then I increase this counter, the internal state of the variable, to the next value, and then I actually return the next value. And with that, I'm able to proceed once I'm calling the next method again. Yeah, so I will not be returning 7, 7, 7, but it will be 7, 8, 9, 10, and so forth. So there you have to be careful when you start implementing those operators. Okay, yeah, that's how you implement pull operators. But if there's a pull, there's also a push. So far we looked at an interface like that. And basically, yeah, that's what we already had, open, next, close. This next interface returns an element. So if you look at that from outside, basically you could also name it a producer. Such an iterator produces data and returns it to the caller. I am calling this iterator, it returns a chunk of data to me. The inverse to that is a consumer that receives a chunk of data. And that is depicted here. The only change is here the chunk is not returned by the next call, but I pass it to the next call. Yeah, I don't expect that this chunk to be returned, but I'm saying here's some data, do something with that. Now, that's a push-based operation. So in the pull-based world here above, I'm really pulling. Give me some data, give me some data. I want to do something with data, produce the data. It's pulling data from that operator, from that producer. Whereas in the push world here, I'm pushing data into the operator and tell the operator, here's some data, do something with that. Yeah, so that's the inverse of the pull-based world. And I depicted it here with a disk, with a filled disk, that's a producer. And this circle here, that's a consumer. And well, if you do that, you could also, I mean, if you have a producer here in the pull world, there should be a consumer in the pull world as well. So, and if there's a consumer in the push world, there should be a producer in the push world. And how do they look like? Well, that's this slide. So basically, a consumer in the pull world doesn't have a next interface. And the same is true for the producer in the push world. It doesn't have a next call. And you will see in a moment why that is must be like that. I have examples in the moment. Just for completeness, maybe let's remove this. We will see operators that have both roles at the same time. They are at the same time consumers and producers. So maybe let's look at an example. So let's look again at an example how that looks like in the push-based world. So again, here's our plan, and how would that be translated? Well, basically here, the leaves produce that data. Yeah, the leaves produce the data here and push them to their parent nodes. Well, and those parent nodes consume the data and then eventually also produce data for the next node. So all the internal nodes in the binary tree are these, I coined them prodcons. Yeah? They have both roles at the same time. That's depicted here again. So that's the same time producers and consumers. Yeah? That's what you see here. Eventually, on top of that, there's someone that does not produce data, just consumes the data that is produced by that tree of operators. Yeah? So again, recall this topmost operator, the simple hash join in the actual plan. That's this one. That's this prodcon, consuming stuff but producing stuff. But on top of that, I created another artificial consumer that receives all the data that is being produced by this topmost operator. And that's how it looks like for push-based operators. But that's also how it looks like for pull-based operators. So conceptually, we can see whether we're talking about push-based or pull-based operators, the roles in the pipeline do not change. Yeah? The leaves are always in the role of producing the data. There's something on top that's consuming all of the data being produced typically the user interface or your SQL shell that shows you the result to that particular query. And everything in between is in this double role of being producers and consumers at the same time. But that is orthogonal to whether you're using a push and the pull model. So the interesting question for after the break will be why? Why is there a push-based interface? Why is there a pull-based interface? What are the pros and cons of the different approaches? And with that, let's enter the break. We will continue at 1:10. I will be available on Discord. See you soon. Okay, let's continue. One clarification, one little bug fix here on this slide, where we looked at the first call to next in this graph. There's a little bug here. This here doesn't have to be necessarily B. So B would be all the elements in B. Now recall, we have the sort order here defined on ID, but we're filtering on a different attribute, A3. So we still have to draw all the elements from that isim level access from the index. And that helps us here in the join, because the join is with respect to this ID attribute on B. So no other sorting is required. However, only some of the values should be used here. Some of them are filtered out, but they're still in order, of course. If I leave away stuff from a sorted sequence, I pick some of the elements in order. So I still have a sorted sequence, obviously. But this doesn't imply that I draw all the elements for this one next call. It depends again on the selectivity. I simply have to draw, so for every element, for every next call I'm issuing on this filter, for every next call here, it depends on the selectivity of this specific attribute, how many calls I'm issuing here. So again, this is can be one, only one, at least one. In the worst case, it can be B plus one. But it doesn't have to be strictly B. I will fix a slide and upload a fixed version after the lecture. So with that, we were at push versus pull. So we looked at this. We learned so the role of producers and consumers don't change. It's independent of whether it's push or pull based. But now let's look at how this is executed, in particular in push-based operators. So here is a graph showing, here's a visualization showing that. Assume we had a push-based organization. Basically, this similar to a topological sort on this binary tree. So the first step, what you will be doing is you will execute this stuff until the first pipeline breaker, until the first time where you materialize the data. That happens here in this hash table. Yes, that's the first materialization point here. Yeah. Here's another materialization point in sort, as I explained to you in the first half of today's lecture. For sort, you have to look at all the elements anyway. So basically, you're buffering all of the elements in the sort operator. So these two things are executed first in push-based operation. Basically, you can do that in any order. Doesn't matter whether you do first this or that, or you do it multi-threaded, but you have to do these two things first. So once you're done with that, the next operation you do is you could push the data to the merge join conceptually. Yeah, which again, if you think about that, if you push all the data available from the sort operation, you replicate it into the merge join, at least conceptually. So if you had a terabyte of data that was stored in the sort operator here, you now store the terabyte of data in the merge join. You push it to the merge join. Of course, you could do that in better ways. You could also do it, for instance, by just passing somehow a file handle or whatever handle to the data around. Previously, the handle was available here. The data belonged to the sort operator. Now the same data and the same place belongs to the merge operator. That would be a smarter way of doing that. But conceptually, you actually, if you have no other means, you're copying the data in the push-based world. Then comes the third phase, and that's the actually streaming phase. So here, there's no need to buffer data anymore. So basically, you read the first element. You pass it to the filter. Once an element qualifies, it calls next on its parent. Yeah. Once this merge join produces a join result, recall all the data from the left input is available in the merge join in this world. Yeah. So basically, you can probe against that, eventually produce a join result that can be used for probing in the simple hash join, and eventually that may produce a join result. Yeah, but at no point in time in this third phase, there's a need to store more than one tuple at any time. So there's no blocking behavior here. So you see the processing of the data is from bottom to top in the push world, whereas from in the pull world, it's from top to bottom. It's the other way around. So another way of seeing that is if you think about the control flow in your program. So basically the control flow in the push world is that the leaves are pushing data towards the root node in that tree. Yeah, that's what we're seeing here. Those are the leaves pushing it into the parent node. This leaf pushes it into the parent node, and so forth. Yeah. So once you're done processing on one of the leaves, you can basically conceptually remove it from the tree, yeah, like in topological sorting. And eventually, you're in a situation where you can stream the data through the what's left from the tree, and then you're done. Yeah, that's how you process data in the push world. Yeah, memory requirements, again, here's what I just explained. So these segments operate until the next pipeline breaker. Again, simple hash join. Here's a hash table. Here's sort, buffering all the data. Or here, the merge could buffer all the data. And here there is no extra requirement for that. So before looking into the next tuple, let's think about it a little bit. So then what? What are the pros and cons of the push versus the pull model? Well, on first sight is you would say the pull, and maybe we can, if you go back to this world here where we had here. So if you look at this graph, one thing you're seeing here is if you're pulling the data from the user side, basically the idea of that is you only perform as much work that is required to perform the next result. And then you start processing. So you try to organize your query pipeline in a way that only the work that needs to be done is actually done and not more than that. Why would that make any sense? Think about that. Why would I want to organize my pipeline in a way that I call next a couple of times, yeah, and for every next call I try to do only the necessary work and then I stop. Maybe I do a little bit more than the necessary work, whatever, but I don't process the pipeline to completion. I don't compute the entire query result at once. I just try to compute what's necessary in order to be able to answer the next call. Why would that make any sense? Think about that and write in the Discord channel. Now someone is writing. Let's wait for that. So you're saying it's efficient with respect to memory and energy consumption. How exactly? I mean, if I want to compute the entire query result anyway, I mean, why do I organize it like that? I mean, I still buffer the entire relations as part of intermediate results anyhow. So what else could be a reason for that? What is it that this allows me to do? Oh, no idea. I mean, the assumption here that might be misleading here at this point is that actually, oh, there's someone still writing. No, okay, I will wait for that. No. Still writing. The assumption that might confuse you here is that is it really true that the user will is it really true that the user will need the entire result set of the query? Yeah, if your assumption is the user needs the entire result set anyway, I don't need a mechanism that allows me to interrupt the pipeline, because I know I need all the result set of that query. Whatever the size of the result set is, I don't care. So why would I do that? Yeah. So that's one concern. Maybe the user only is interested in the 3 of those tuples. Maybe they're sorted anyway, and the sort order already gives them a rank. Think about Google. Did you ever inspect all of the results of a search query in Google? You don't do that. Yeah, you look at the first 10 results, the first result page. Maybe on a bad day, it's the second page of Google as well. I rarely go to the second page on Google, so the first page is really interesting. Yeah? So the first 10 results may be really interesting, and everything else doesn't even have to be produced. And the same holds for Google, by the way. So if Google tells you, hey, I found 5,789,355 results. No, it didn't. Yeah? That's just an estimate. It doesn't produce those results, it just gives you the first page. And only when you click the second page, these other results are produced or need to be produced. Yeah? But there's no need to produce these millions of results. Yeah? And the same can be done here. If meaningful sort orders can be exploited, and we have a sort order C on the merge join, so that may make sense. That may represent a ranking of importance, or a good fit to a search query. So that's one thing that's important. Why you want to do something like that? In SQL, you have that in the limit clause. You can say, give me the result set, select star, tra-la-la-la-la, join conditions, limit, depends a bit on the database system. You can say limit only to, just give me 10 results. So then you can only compute 10 results and don't have to compute all the millions of results that follow. So that's the major reason for doing that. And then your energy efficiency comes into play, saying, okay, if I only need the 10 results, I don't waste any energy for computing 11 and result 11 and everything that comes afterwards. Then it's an important argument, I understand. The other could also be, in terms of a user, how is the data, how are the results passed on to the user? Yeah, and that's a very similar argument, but basically, if you process this query plan independent from the user, you produce the millions of tuples of results. Again, you may have a problem that you still have to keep them. You have to materialize them somewhere, either on main memory or on disk. Yeah? And if it's a large result set, that may be a big waste. Yeah? Just to keep all that result set of the query and hoping that eventually someone, the user, will look at that. Maybe he or she will never look at that anyway. So that's another reason for doing that like that. So that's a big reason for doing that, being able to limit the amount of work. And in particular in analytical scenarios, so where people use analytical databases, you often have a very iterative style of exploring the data. So you somehow analyze data, you use SQL for that, you either by writing SQL directly into an interface, or you have a click and point interface where you can draw attributes to columns and rows and pivot tables. And that in the back there might be SQL generated. But basically there's a lot of trial and error. Yeah? You try something, you see the first couple of results and you see, no, that's not what I was looking for, right? And then you discard the query, you slightly modify the query. You try it again, you execute again, and then you see, oh no, it's still not, oh, it's better, it's not what I'm looking for exactly, but it's better. You still tweak the query again. Yeah, so it's a very iterative process, and it would be insane to compute the query to completion if that query produces many query results. It's a different story if the query aggregates. If you only have few result tuples anyway, then other techniques apply there. Okay, So that's basically what I wanted to say about that. So push versus pull. You will also see those pull-based interfaces are used heavily in disk-based database systems. So that started in the I think in the 80s already, when people were started use that. Main memory systems mainly use push-based interfaces these days. The same also is true for our system, Mutable. It's push-based organization in its interpreter. What else can we say? When you look at sensor data, you will also see push-based interfaces like that. There you have sensors. Yeah, the sensors measure something like the temperature, and they push it somehow through the pipeline. So basically, control is with those sensors. So this pair, of extremes, pull and push, has a lot to do with who has control in such a query plan. Yeah? So in the push-based world, basically control is with the leaves pushing it to the parent nodes, which can then do something with that. Whereas in the pull-based world, control is with a topmost node, which delegates control to its children in order to produce results, and then being able to continue processing. Yeah? That's a major differentiation. In any case, data flows from bottom to top. Doesn't flow from top to bottom. So like in any relational algebra expression we've ever seen, it's always from bottom to top. But the difference is more about who controls the computation, who decides what is being done next. Okay, with that, we will move to the next topic. And that's a fancy technique allowing you to speed up column stores or queries that operate on column stores. And what we will learn about is something that is the inverse of the projection. So projection leaves attributes away, and anti-projection adds attributes to an existing schema. Why would that make any sense? That's something we look at now. So let's look at this situation. Let's assume that our data is in a column layout. And I don't have any join among relations here. What I have is simply a single table T. I have two where conditions A equals 8 and B equals 5. So again, in relational algebra, it looks something like that. So selections can be in any order. This is the input. And here's a projection projecting to B and C. Right? That's relational algebra. But what does it mean in the column store? Well, actually, yeah, conceptually, the data is a relation. Yeah, but if it's a column store, it's kind of split into like these columns, which independently could be considered relations of their own. So basically, I could say, well, actually, what I have is something like that. I have a relation that just keeps the attribute values of A. Of attribute A from T, attribute values of B from T and C and so forth. Actually, it's not talking about one relation as it looks like in the SQL statements. Actually, we're talking about three relations here, right? You have the different attributes. So programmatically, what I would need to do is I have to join those relations. Yeah, and that could be along any concept. We had this implicit and explicit column organization. In the easiest way to organize your columns is in an array-style representation, of course. Yeah, so you have all columns have the same length. Maybe they have all 42 tuples, and if you are in column A at position 12, and you want to know what is the attribute value of B for that row, well, you go to this column B at position 12. Yeah? So they're all at the same position, at the same array index in those different arrays. But conceptually, what's happening here is you have to do a join. Yeah? You have three separate relations, each holding data for the different attributes, and you first have to join them. Yeah? That's basically what needs to be done. And the simple way of doing that is what we see on the right. So we know we need A, B, and C. We need A and B for filtering, and actually, eventually we have to project out C, as C has to be displayed to the user. So, okay, we get all the attributes we ever need, A, B, and C, join them based on that array index, yeah, that's, I call it the row ID here. That's a database term. It's basically an identifier for a tuple in a row, allowing me to directly access a specific row using a physical address. You should never use that in a query, in a SQL statement. That's just an internal thing, like the array index here. So, but based on the array index, I can do a merge join. That's already sorted along the array index, naturally. Not much to do here. Then I filter out, and then I project it out. And this way of putting the data back together in a column store is called early materialization. Early materialization in the sense that actually at this point in time, at this join, I form something that looks like a tuple with 3 attributes, A, B, and C. And then I do a row-style processing on those tuples. That's early materialization. Sorry, I need some. So here we are. Well, and what you could do instead is something like that. Because in this particular query, in order to identify which rows qualify from T, yeah, well, the only attributes I ever need to make that decision is A and B. I don't care about C. C is something to be displayed for the user eventually. But just to decide which rows qualify, I can do something like that. I push down the selection here. So I read column A, filter out the rows that qualify, and just keep the row ID, the array index in this word. I do the same for B. Yeah? I filter out the rows qualifying. In addition to this row ID, I also keep the actual value of B because I need it later on for the user to display it here. We have the B here. Then I again perform a join on the row IDs, which means I put these attribute values from A and B together into a tuple-like structure of A and B. And then what's missing is, well, at this point in time, I know the row IDs that qualify. I evaluated the entire where condition. What's missing is a C attribute. So there's a C attribute that needs to be displayed to the user. And that's what I'm doing here with this extra join here. So this joins the row IDs that survive this join with the corresponding row IDs from C. And that's basically just adding this other C column that I need to display in the projection. Yeah, the standard projection I'm having here. So what this projection does is it basically removes the row IDs, internal row IDs are used in that representation. So this operation here that basically given some sort of row ID, some row representation, adds another attribute from a table is called an anti-projection or late materialization. So rather than, let's go back, here from the beginning, before I do anything meaningful with the data, I join the 3 columns together with that join. Now I have a tuple-like structure with the 3 attributes A, B, and C. And then I do all the filtering and projecting. That's early materialization, early putting the different values into a row-like structure. In contrast, in this world here, I first do the selection and then I do a late materialization. I extend the schema by attribute C using this join, and that's an anti-projection. Right, so there's a question. It's efficient with respect. No, that's an old question. Yeah, something's wrong with my Discord here. Okay. Okay, and this is actually a partial late materialization because a more extreme way of doing that will be something like that. So what's the change here? Here I'm saying, so look at that again. Here for B, I identified the row IDs that qualify, but also kept the attribute value of B. Yeah? So what I could do in that case, I could say, no, I first do this left part here. I just identify the row IDs that actually qualify, and that is the same thing as doing an intersection on these streams of row IDs. And then in an extra join, that basically takes as input, it's actually a 3-way join here, the row IDs that qualify. and then joins that again with this column B and the column C. Maybe some of you can think about what the drawback of this may be. Yeah, if you do it like that rather than this. It's actually already visible in the graph. There's one drawback here you might identify. But that's definitely, this is a more extreme way of doing this kind of materialization. But what might be a problem with that? Well, one problem is that this column is read twice, right? I have it in my hands already. In order to be able to evaluate this condition, I have to read the values. Yeah, the advantage I'm having is I don't have to keep the values from B in main memory. So I don't need to do that here. I don't waste, depending on how the pipeline is organized eventually. So I don't have to keep the values from B at this point in time. Yeah, there's no memory I need to consume for that. However, once I do this join, I have to reread the entire column again. And maybe that can be streamed. So the advantage will be I don't have to store the values from B, but I have to read it again. So this means reading the column again. I mean, think about that for a moment. If this is a merge intersection anyway, those streams are ordered by row ID. So that at no point you have to materialize anything in main memory, which means that basically there's no need to materialize anything at any point. So this pass doesn't make too much sense. I would probably go for this one. Yeah, there's none of this is blocking, so you have it in your hands, you pass it on already. That's how I would do that. But anyway, so how you could depict that is really, it's the inverse of projecting, and that's why I put it upside down. I could also have written a pi -1 or something like that, but I thought that this would be nicer. So you have a relation with 3 attributes, A, B, C. You project to something, then you have here maybe AB. Yeah? Something smaller typically. If you project to the same schema, okay, you can do that, it's allowed, but doesn't make any sense. And this anti-projection is the opposite. You have a schema, say A, B, and you add a column to that, an existing column that originally belonged to that relation, wasn't there, but now you add it again. So projecting out data is about the question when to narrow tuples, and the opposite is when to widen tuples. Yeah, here's an example of how that will work in a column store. So assume the following scenario: symbol select star from T. That's our relation with 3 columns, A, B, C. That's the query you have in the column store. Row-wise input would look something like that. Yeah? Column-wise input, something like this. So how would you process that? In early materialization, you would do the following. So it's a column store. That's what we find in the data, the database store. So these 3 columns. But in this case, you early materialize. Yes, you put them together. Yeah, basically join them together in a row-like representation. Then you filter out the stuff that actually qualifies. So that's where A equals 8 and B equals 5. That's this single row in this word. In contrast, in late materialization, for this example, we are on a column store. We select A and B only. So actually, we only have to read A and B for the moment. Basically, what we create at this point in time is a bit vector marking the qualifying entries. Yeah, so maybe bit vectors we already had when talking about bit maps and bit lists and indexing. So it's a similar thing being done here. So basically, we create a bit list that is the output of this predicate. Yeah? So for each entry in this A column, we record whether it qualifies under the given predicate. Yeah? So we record whether A equals 8. Well, that's obviously false, true, true. Yeah? So 0, 1, 1. And here we record whether B equals 5. Well, that must be false, true, false, obviously. And that's the result we obtain here. Then we logically AND them. That's basically happening here. 0 and 0 false, 1, 1 true, 1, 0 false. So that's the result here. So we do bit list operations as we did it in on bitmaps. And then we continue here. So we have this one. And now we do the actual late materialization. So basically we can now read all of those three structures at the same time. That means column B, column C, and so recall here we only had three entries in those columns. It's an example that fits on the slide. So basically we read all entries from B, all entries from C, and all entries in the bit vector. You can stream that, of course, perfectly. And then you only keep the ones where the bit vector is set to true, to 1. And that's only this one. And then if you want, you still have it here in column layout, but if you want, you can put it into a tuple-like layout, depends on who's consuming that. And that's your result. So that's how you could do late materialization. And here's another example where a join is performed using early materialization. So assume two relations with attributes relation T with attributes B and A, relation S with A and C. Here's the SQL statement. So we join those together along that A condition, that's this one. And then we receive this, still carrying the join key A. Then we project it to B and C. If we do that with late materialization, it could be something like that. So basically we execute the join T.A, that's the condition T.A equals S.A. But what do we keep here? We basically keep the positions in that form a join result. So how should that be read? So here we have two entries, positions from T.A and positions from S.A. So this says the tuple at row ID 0, at position, or at every index 0, matches with a tuple from S at position 1. So if you look at the data here, we have a 3 here and a 3 here. Those two match. That's the join result. And that's basically what we record here. So each entry, each row in this structure describes the join result. So the next entry is position 4, 0, 1, 3, no, here we have an index anyway. So this 2 matches with 0 here with this 2. Yeah, those two, that's the join result. And then the 5 and the 0 is the join result. So I keep the row IDs across both of those relations that match. And that is called a join index. So I didn't produce the actual join result in the sense that I kept the attribute values that I'm interested in, but I just kept positional information on which row from input T matches with which row from input S. And those that information is all sometimes some database systems, in particular disk-based systems, used that heavily in the 90s, that you pre-compute the corresponding tuples. And now if a join comes in, of course, you can exploit such a structure. You don't have to compute the actual join anymore. You just have to go through that join index, through that positional lists to complete the join. But this is a structure that can also be used in late materialization, because now what we do is we have that positional information, and now we can apply an projection doing something like that. Actually, this projection here is, of course, not required, because it's only required to filter out those row IDs, of course. So after adding the attribute values from B and C, you want to get rid of those positions because they are internal positions. They mustn't be exposed to the outside world. So what you first do is you add columns B and C, the attribute values from B and C. That happens here. And then you project them out to, the raw IDs out to get that result. So that's one way of doing that. So what are the pros and cons? Early materialization. The big advantage is you have no re-access of columns necessary. You've seen that if you evaluate a column if you read a column to evaluate a filter condition, and then later on you read the column again for materialization purposes, you access it twice or maybe even more times. So it's much easier to just read it once and keep it. Well, you read it anyway. It's easier for planning. If you know, okay, I need those attributes are required during query processing, or those attributes have to be shown to the user. So it's much easier to do early materialization. However, what may happen is that you need more memory, wider intermediate results, which are not actually required. So you can really bring down the memory consumption of such a plan. I mean, it's not a technique. So if you start implementing a query processor, you will definitely start with early materialization. It's so much easier. But if you want to lower the pressure on what you keep in memory, you can consider late materialization. Because here, you only construct tuples when necessary. And yeah, this is actually a drawback that should go to disadvantages. So slightly more complex planning, and reaccess of columns is possible. But you lower the memory pressure that may happen. But it's like a second concern technique, not the first thing you will be thinking about. It's something you do, it's the second or the third step, but it may have an impact. So that brings me to the summary for today. So we've seen there's blocking behavior of certain operators, and that's a principal problem. Yeah. So for sorting, for instance, I mean, it has nothing to do with the actual sort algorithm you're using. It's a principal problem. If you want to determine in a sorted stream what is the first element, same for the minimum of an input stream, you have to inspect each and every element. You have to look at it at least, or in the context of these operators we introduced today, you have to buffer all the data at some point. And there you have to be careful with memory requirements. Yes, some operators have that requirement. They have to inspect the entire data. That not only you need a lot of memory for that, but also it may then block the pipelining effect you may expect from if you hear the word pipeline, you might expect, well, eventually some data will flow, right? But if someone is breaking the pipeline, like sorting or creating certain indexes, that may require a lot of time. And that time you have to wait, because in that time, no result will be processed by your query plan. And that may be a problem. We looked at pull versus push. So this pull style or open next close ONC interfaces, they're widely used in disk-oriented systems, as modern systems are main memory database systems, or even other storage media. They use push style, which are also a bit more favorable because they are data-oriented in main memory and not so much function-oriented. One thing you should do when using those pipelines is to use batches. So don't pass individual tuples around. That, if you want to lower the memory pressure, yeah, that's a good idea, yeah, because then you will get to the minimum of intermediate results you ever need. But in order to balance that out with an efficient overall query plan with a good query response time, you probably want to experiment with batches. A batch is a set of tuples being passed around with a single call, be it in the push or the pull model. And that typically gives you a good trade-off. The size of a batch is a different story you can experiment with, but the size of a batch being just a single tuple is typically not such a great idea. Yeah, that's it for today. That's all I wanted to tell you about query optimization, query processing. I will be available on Discord and the audio channel. Other than that, we will meet again on Friday for the lab, 12:15 again. The assignment will be available today in the late afternoon. And we will look at that on Friday. With that, stay healthy. See you soon. Thanks for your attention. Bye-bye.